Is it done? I request all of you to please switch on your cameras for a moment. Thank you so much. Honorable Principal Ma'am, respected guests, senior faculty members, my colleagues, and my dear students, a very good morning to all of you. It's indeed a matter of great pleasure for me to talk on this day. We all are here today for the celebration of Science Week from 22nd to 28th February, which has been sponsored by Department of Science and Technology and Renewable Energy, Chandigarh Administration, Chandigarh. We all know National Science Day is celebrated on 28th of February each year to mark the discovery of Raman effect by the great Indian physicist Sir C.V. Raman. This day is being celebrated every year to widely spread a message about the importance of science used in the daily life of the people, to display all the activities, efforts, and achievements in the field of science for human welfare. It is celebrated to discuss all the issues and implement new technologies for the development in the field of science, to give an opportunity to the scientific-minded people in the country and to encourage the students as well as popularize science and technology. So with this agenda in our mind, Meher Chand Mahajan DAV College for Women under the aegis of MCN Vigyan Manch has planned series of events for the complete week to enhance our knowledge for science. Starting with our very own Postgraduate Department of Chemistry, we have organized this webinar for today. So let me quickly introduce you to the speaker of the day, Professor Ashish Paul, Scientist F, Institute of Nanoscience and Technology, INST Mohali. He has done his PhD from Department of Organic Chemistry, IISc Bangalore in 2009. He was a postdoctoral research fellow from 2009 to 12 at University of Technology, Eindhoven, the Netherlands, and he did another postdoctorate at University of Groningen, the Netherlands from 2012 to 15. His research area is majorly focused on development of supramolecular polymeric hydrogel-based biomaterials for ECM mimic and tissue engineering, stimuli-responsive materials for controlled release and delivery, dynamic combinatorial chemistry for self-healing and functional nanomaterials, multivalent recognition for imaging and diagnostic application. He has 31 publications in international journals, 1 book, and various conference proceedings to his credit. Today he will be enlightening us with his views on nanotech and future implications. I heartily welcome you, sir. Over to you.
Thank you, madam, for your kind introduction. And at the outset, I would like to thank the convener and the coordinator of this interesting program at your college. And so it is very it is always heartening for me, to discuss with in the college and school students, because I do see keenness and a future, of the country in them. So I think what I would do first is that let me share my presentation. All right. So I hope the screens are visible now, full screen. Yeah. All right.
Yes, sir.
Yeah. So today I'm going to talk about nanotechnology and its future implications, and I'm sure that all of you by now have heard about this term nanoscience and technology. And this is the building. What you see in this picture, that is actually Institute of Nanoscience and Technology, and this is the only one dedicated institute in entire country which has just come up in 2013. And the new campus, you see this new building, we have just moved in 2021, last year. Yeah, so this institute is dedicated for doing research on nanoscience and technology. All right, so what I will do in this class now, in this particular lecture, I don't want to keep it very formal. Okay, let it be informal so that you can actually grasp as much as you could, or more than you could possibly. So what I would do as I go on for this almost 45 or 1 hour lecture, what I will start with some of the basics of nanoscience. Why and nanoscience, why is it important? Okay. And then we'll look at different implications around the globe, how nanoscience is so important, and it is actually, making the scientist drive towards this particular research area. Why is it so important? So this is what we'll do for half an hour or more than that. And at the end, we will see how INST or our group, we are contributing towards nanoscience and technology and what we are making. So that will be rather a little more specific, but I think you will have definitely a lot of fun in first 30 minutes or so, listening to various interesting aspects, which would, I believe, that which would actually bridge your textbook knowledge or whatever master's or undergraduate course you are studying with cutting edge research or the inspiration towards cutting edge research. All right. So with that, let's get starting. Let's get started. And then what we do see, first thing is that today's trend is research and development. If you look at, and let me get the pointer, you will see that nowadays, I mean, initially, if you follow the red trace over here, you see that after 2000, after the year 2000, there is a tremendous growth and opportunity in the nanotechnology related work. And after 2010, you see that this particular curve has actually shot up because rapid advancement has happened on nanotechnology in last 1 decade. And now many of the nanotechnology based products have started to come in market. And I think you would be very, very certain that you have really come across multiple, products in the market which are based on nanotechnology. However, if you look at 50 years ago, yeah, there was only some basic research of nanotechnology, but people probably did not also know about nano, the quote unquote nano, this particular term. People were doing something relevant, but they did not know that is really nanometer dimension. All right. So nowadays you see nano means what? It has to do with the nanometer dimension or nanoscale, time scale, something like that. Okay. So I'm coming to that. But before that, let's look at many of these, information technology. So you see these small little chips, in computer. This is much more information you can actually, store in that. And this is possible because this has become smaller in size. Similarly, you see that, there are these solar cells, which you have been already seeing as a source of renewable energy. This is also something to do with the nanostructured material. And nowadays, you will see later on, you will have something called flexible electronics, which will come. So your solar cell might be like that. Your mobile phone might also get so flexible that, mobile phone, you may not have to charge. It might draw, charge from the solar cells. It's possible. Similarly, you get to see these electric vehicles are coming, and already in Chandigarh, you get to see these, electric buses are flying, right? Similarly, many of the medicines, now if you start look at the composition of the medicines, many of the companies have started doing nano formulations in that medicine formulations. So these are very interesting. And then also disease diagnostics or drug delivery, these are all has to do with nanoparticles. So these are all different fields which has really revolutionized. Eventually you see the consumer goods. So I think, many of you would remember, if you have seen 1992 World Cup, probably not, that was the time we first time saw that, Alan Donald was bowling, and then he was putting something white on his, on his cheek. And we did not know what are this. Then we learned that is something white. Oh, that is something zinc oxide. And why people were using zinc oxide? Well, just like you use this sunscreen lotion and all that actually prevent the sun to come in, like that also many of these nanostructure powder people did not know, but then they saw that these are, if they are colloidal or nanoparticle like thing, they kind of screen many of these UVB, UVA, such kind of lights. So people were doing it, and these are all actually included in the consumer goods. So a lot of things which happen to us knowingly or unknowingly. Okay, now the most important thing is that we should know that what is nano dimension. So nano dimension, you can, if you want to give you a feeling about the first discover nano materials, which was actually fullerene or C60 buckyball, also many people used to say. So if you look at a size comparison, like if you have our earth, right, the earth, if you can actually make it into small 10 million small pieces, okay, then that one particular piece is actually equivalent to one football. Okay, right? Football is something like 22 centimeter or something like that, right? So now similarly, if you take one football and you make 1 crore pieces, 100 crore pieces, and then 1 billion pieces rather, so then one of the piece will be your fullerene. That is the size comparison. Now you can consider, if you consider a football and your fullerene, how small it could be, right? It is 1 billion times smaller. So typically, and you can see this is like 0.7 nanometer. That's the size of a fullerene. Now, if you look at, so this is the scale we are talking about. Nano means 10 to the power 9 meter. That is the scale we are talking about, of course. So typically, I mean, for classical nanoscientist, we can call that, okay, I'm working on nano dimension. That means, or I'm working with nanomaterials. That means the nanomaterial should be, strictly speaking, between 1 to 100 nanometer in size. Okay, or I mean, many people nowadays, you will say that I'm making some nanoparticle or something like that. You will see that that may be, in 400 nanometer, but people still will call that, prefer to call that, oh, this is a nanomaterial. Even though I know that that is actually like 0.4 micron. It's more micron than the nano, but I think there is no, strict border between nano and micro, but people can wish to call them nano, they can call. But I think strictly speaking, I would really be interested in looking at this particular dimension, which I have mentioned on my screen. But it's not only about dimension, it can also be about the time scale. If some phenomena is happening very fast, okay, normally if I am moving this hand, you see, this is happening in second time scale. But if you can have it, if I can move this my hand in very small time scale, like milli time scale, then micro time scale, or maybe in nanosecond, then also this has some property which would also have an implication in the nanomaterials. So it's not only the dimension, sometimes the time scale that also contributes to the nanomaterial, right? All right, so now we know about the dimension and time scales, all these things about nano. The first introduction about nano is done. But then let's look at what happens when you go for a nano. So first thing comes in your mind when you see this picture is, what is this? This is gold, right? And this is what you get to see as a gold. This is gold. So, we wear jewelries and all this. So these are all, this is the color you see, right? But what happened, this is a bulk gold. Okay. Now gold means, what is this? AU, right? All of you know, I think all of you are chemistry students. So that is AU, zero state. Now these are all bulk gold. Okay. But what happens over the time, scientists, they figured out, if you can break these golds in small little pieces, very, very small little pieces in nano dimension, what happens is that you can actually get into colloids and you can actually tune the color of the gold colloid, which are again AU plus on AU only, okay? But these are all nanoparticle or gold colloid, and based on the size, you see the smaller to little bigger, you can tune the color of this gold nanoparticle. That's very interesting. So physically speaking, we being a chemist, we don't keep on breaking the gold. What we do is that we take a gold salt, okay, and gold salt, which will be in AU3 plus. We actually use sodium citrate as a capping, and you also, can use a further reducing agent like sodium borohydride or something like that. What you do is that you convert this gold 3 plus to gold 0 state. Okay, now what happens is that the sodium citrate will have a lot of this citric acid, right? So it will have this COOH group, which will cap this particular gold nanoparticle. Cap means it will not let this gold nanoparticle or the colloid gold to aggregate into bulk, and it will make it very stable colloidal gold nanoparticle suspension, and that's how you can actually control the size depending on the concentration you choose, and you can make this nice gold nanoparticle of different color. This is the thing I was saying. You take metal precursor, you reduce it, and you form these clusters, okay, and this is how you form the gold nanoparticle, and that's very nice color. Now you have made it. How do you know it? You can see definitely by, if you take an spectrophotometer, you run a UV vis signature, UV vis, you will find red color, you will find a particular wavelength, right? This probably you have studied UV vis, right? You will get a signature. You can also do a microscopy, and this is something very unique. This is not a normal microscope. You need to see this kind of nanoparticle through electron microscope. So this is a transmission electron microscopy. And you can see these nanoparticles, small little nanoparticles, which are like almost like 15 nanometer in size. Okay, you get it? I'm going to discuss about why. You might also ask why we cannot see these nanoparticles through optical microscope. That you might have a question. I'm going to answer to you in 1 or 2 slides. Okay, down. Now, what is interesting, what you find? So what you find is that definitely whatever bulk material you see, that has a completely different property than the nanomaterials of the same material, right? You see, this was a different color, but this has completely different color. That's the first thing. And what is the other thing you see? The surface to volume ratio. As you keep on making the smaller particle, it will have a much bigger surface area with respect to the same volume, right? So because of the surface to volume ratio drastically changes, what it does is that this eventually becomes a surface phenomena. And because of this surface phenomena, many of these interesting, through quantum mechanics, if you have studied, you can actually have many of these, quantum material. This becomes a quantized, or some people also call very small one, so you can call that as quantum dot. And because of that, many of the property which comes, there is something called surface plasmon resonance. That is why you actually tend to have this kind of band. So you have this, the quantum mechanical band creation and band gap energy come into picture. I'm not going to come into all these details, but these are, definitely physics behind it, and you can read it as, or maybe you already know, or you can read it later on when you go for further study in your masters. So definitely what I meant is that bulk gold and surface nanomaterial based gold, they're completely different. This is something, is a takeaway from this slide for you. All right, but then when we looked at history, and this is what we are doing now regularly, there's nothing so big deal. But you see, this kind of, the gold nanoparticle formation, this actually happened earlier also, but we did not know that it is a gold nanoparticle. People were amazed seeing that, oh, there's nice things. So if you look at in British Museum, London, if you go, there is this Lycurgus cup, and you see this cup is very nice, and this cup has this glass impregnated with this very nice gold nanoparticle, and that's why it was red in color. Even in earlier days, you used to have these, this Roman Catholic Church and all this. So you used to have this very nice window of the church, and we always used to think, what? I mean, you must be putting some color or pigment through it, but actually it's not so. It is actually gold nanoparticle of different size, which were actually impregnated in this glass matrix. That is why it was giving interesting color for this, right? So these people, without knowing that they are nanoparticle, people were just, okay, making it, something happened. Okay, we got it. So let's put it. It's very nice, colorful. That's how people were doing it. Even if you look at in our Indian tradition, we also have these bhasmas people put, and then eventually if you look at, there's nothing but, what bhasma is, what after yagna you have, something black color stuff which is remaining. But in fact, nowadays people are using this technique like in furnace or stuff like that, and what you get that is actually graphene, right? So that is actually very good conducting material. So yeah, people are also getting these carbon dots. So these are all things which did not know, but now I think we are coming to know. We are trying to explain the logic, what is this and all this. So the real scientific beginning of all this historical perspective that I'm saying, that started in 1857. This is the boss, Michael Faraday. He initially termed that, okay, these all colored material, that probably is due to the colloids. So that's how this colloid field that got introduced. And we also know later on that blood is also a colloid, right? And that's how, when the blood gets clotted, how do you clot? I mean, if there is a cut, you profusely bleed, right? Then you actually have this fibrinogen and all these that actually trap that blood. So we need to understand how the colloid came, and that's how the scientific beginning for this nanomaterial started. There was also another, after almost 100 years, there was a famous lecture by Richard Feynman. Okay, there he said, in that particular lecture, he was predicting that, he is a very classical physicist, of course you must be knowing. He was saying in a lecture that there are plenty of room at the bottom. That means you can do a lot of things with the small little, bottom means if you go for top-down approach, the smaller material, you can do a lot of things. That means nano terms got introduced only then. Okay, and people did not know. But nowadays, last 20 years or so, or 30 years, we have got different microscopic technique which has got introduced, something called AFM, atomic force microscopy. Then you have this transmission electron microscopy. We are going to discuss that. That's how our perspective completely changed. And why? Now these nanomaterials become very, very important. And nowadays, in 30 years, you see everything change. And let's say for any country or for the globe, there are also major challenges, right? What are the challenges? One is energy, environment, security, food, disease control. Now, how is it possible? So energy, you all know that energy is limited. Fossil fuels are limited. That's why you have to go for renewable source of energy. So be it solar energy, so to power your house, or be it electric vehicle. Okay, so that's also another thing. A battery, all these e-rickshaws. So that these are important. Or you can also think of something like, you are going for a jogging and you have your mobile phone that is getting discharged. Either you can actually get it charged by the solar. That is possible. People are looking at it. Or you can actually put these things over here, and as you are jogging, what is happening? Your muscles are working, right? So that particular energy, if you can convert whatever you are shedding off calorie from your body, that if you can trap because you are moving, and if you can generate electric energy because of your movement of the body, and that you can charge, then it is like something called piezoelectricity. You are moving your hand, you are generating, because of that movement, you are generating electrical energy. That's a piezoelectricity. And with this piezoelectricity, you are actually charging your thing. And that is a reality. We can do it now. And I can show some of our experiment. We have also shown such kind of things. Now, definitely, if you are using such kind of renewable source of energy, your environment will be very clean. So you don't need to really bother about all these carbon dioxide and stuff like that. In fact, using many of the nanomaterials, people are now sequestering, or not, I should use rather a simple term. So you can actually capture the carbon dioxide from the environment, and you can actually convert into something useful material. And from there, you can make a polymer called polycarbonate. So you can capture the carbon dioxide and use it for making a precursor that you can polymerize. So you can make a polymer, like you use polyethylene. bags, right? Polythene bag. So they are actually ethylene monomer based polymer. Similarly, you can actually have carbon dioxide, and you can actually make polycarbonate sheets. And if you know, in your parking shed, you will see that there are these sheets. They are nothing but polycarbonate sheets. So you can do a lot of stuff. Similarly, security. Terrorists are coming up with, small little, earlier days, you need to have 10 kg of RDX or something like that. Nowadays, you can actually have, let's say, 1 gram of RDX, and you can make it very, you can be very efficient explosive. Now, if you have to really find it out, so security agencies also have to have very nice sensors so that you can find it out very quickly, right? So these are some of the things which are very interesting, and these are only possible if you have nanotechnology as a platform to mitigate such challenges. Similarly, food. Okay, now food is also very important because population is increasing, so you have limited area to do agriculture. So your agriculture should be smart agriculture, right? So that you can have better yield, better crop, and you should not also throw too much fertilizer in the field, because what happens, the fertilizer is going in the particular, let's say, in your crop, and that crop you are eating, and that is actually ending up in your body, and that's what is actually leading to a lot of this disease nowadays, this cancers and all. Because if fertilizers you are giving, you're spraying a lot of pesticides, but if those things you are doing to kill the pest, but that is when it is getting accumulated in your body, that is also harming you. So how we should do is that, can you really think of a solution using nanotechnology, because it has a higher surface to volume ratio, as we have just learned. That means it will be more efficient. So even if at a lower dose of your nano agriculture or nano fertilizers, if provided you can develop, that can be more efficacious. So what will happen, you don't have to throw a lot of stuff in it, and it will be limited, and that's how the food you will eat, that will be also good in terms of quality, right? Similarly, disease control has the same thing. You have a disease, what you do is that you take medicines, and doctor always give you a dose of medicine, that okay, subah sham 2 baar karke aap lo. And if you look at the medicines, let's say paracetamol, because of COVID, all of 650 milligram of paracetamol you are eating, you are taking every time, right? So you calculate, if you have it in 2-3 times in a day, how much you are actually putting in your body, more than a gram. And it is actually circulating on entire blood, and also it is going to the organs wherever it is necessary to keep the temperature down or whatever. Now, can you think of a material, if you can put this drug on a nanoparticle, now what will happen, the nanoparticle will be smaller, and it will circulate more time in your body, okay, and it will stay in the therapeutic window, right? And if you can write a address, just like you write a letter, right? If I'm writing a letter to the principal of MCMDAV, what I will write, right? I'll write principal's name, I will write MCMDAV sector, maybe 38, or I don't know exactly the address. So I can put that, and it will go, right? So it will be directly. It is called targeted delivery. So if you can put some particular signal on your nanoparticle, that it will go only to that particular organ. Let's say you have a problem in the kidney. It is written, the address is written, it has to go to kidney. So you take it orally or by injection, it will go and end up in kidney only. So it will not go anywhere else. So your side effect in the other organ because of this drug will be also less, right? Now, but what happens is that typically whatever medicine we take, there is no address written to it. It goes in your body, and it will actually circulate in your blood till the time it actually body excreted out, right? So till the time it will do, so it will reach all possible organs, and it will create side effects. So this is the reason. And this is possible through nanotechnology to mitigate such challenges. And this is why it is very important. And at INST, we are actually addressing all these different things, be it energy using nanostructured device, or strategic materials, or energy environment. These are taking care of the energy. I being in the soft nanostructure and chemical biology interfaces, we are looking at many of these healthcare applications, then nano agriculture applications. So a lot of these things can be done. Okay. So now let's look at some of the things, because as I said, that let it be first half an hour very general. So another interesting thing about solar cell efficiency, you might always wonder that how solar cell is contributing, and okay, solar cell is there, what is so new? But remember one thing, all the solar cell, whatever you are seeing, which are being put up, these are all silicon based solar cells, right? And the silicon is a semiconductor, right? Because silicon can be N type or P type, right? N type means it is driven by mostly the electron, and P type means it is driven by the hole. So you put this silicon and you make this layer of silicon, so you have this N type and P type. So basically there is a electron deficient zone and you have the hole deficient zone, and that is how actually what happens is that electric current flows. If you if you give a bias, it will start flowing and it generates electricity, right? Upon now this will have particular band gap, and then upon solar energy, it will capture the solar energy and it will generate the current, right? Now what is the thing, what you see is that two important thing you have to note when you are talking about solar cell efficiency. So suppose 100 photons are coming, okay, from sun. Hardly solar cell efficiency using silicon, it can have maybe 20% efficiency. That means only 20 of such photons out of 100 can be converted into electrical energy. What will happen to the 80? The 80 you cannot convert, and that is why you will see the efficiency is very poor. Second thing is that if it is a little cloudy day, so then the sun is not shining bright, so then you will see that your electricity generation will also not be that good. Okay, so then what? And if you are generating that much energy from the solar cell, you can only run what you can run. You can run fan or some lights and all this. But if you have to think of running AC, or if you have to think of running bigger, motors or something like that, what you need is that you need to generate a lot of energy, and that if you have to generate a lot of energy, you need a bigger solar panel, right? And for putting bigger solar panel, you need to have bigger area, but where is the area? So that means what you need to do is that you have to move on eventually from this silicon solar cells to some other new nanostructure material which will have much more efficiency. That means more than 20%. If you look at the silicon solar cell has around 20% or something like that. But if you move on to something higher, if you can double this, maybe make it 40%, then what you will have 40 photon, it will convert into electrical energy. So with the same area, you can actually generate double the energy, which is good. Then eventually you can have solar power AC, solar power cooler, many of the things you can run. And that is where that is the direction nowadays. You can see it is going, and you already have materials which are coming, like 5 junction solar cell materials which are coming, which are like 40% efficiency, which is good. But then there are also drawbacks. Now what are the drawbacks? Is that this particular materials which you are developing, they are moisture sensitive, or if there is a lot of rain, then this will degrade. So it is also not robust. So what you need to think, you need to put some coating. But then if you put coating, then it will not capture the photons, right? So these are different challenges, and which is what actually we have to address. And this is what some of us are also addressing. I will discuss when it comes. So do you understand the challenge? So solar cell efficiency, increase of solar cell efficiency is very important, so that you can run your AC also on solar cells, right? Similarly, what are the other sources of energy? Hydrogen as a fuel. This is a train which is running in Germany, which is running on hydrogen, and hydrogen is better than your what you call is diesel or something like that. But diesel or petrol, what are diesel and petrol? They are hydrocarbon, right? A mixture of butane, pentane, hexane, all these mixture, right? That's what you put. So you have carbon also, you have hydrogen also. But if you have hydrogen, where do you get? Very interesting source. Hydrogen you can get from water. Water can give oxygen and hydrogen, and that hydrogen, if you can store nicely, it can act as a fuel. And the fuel density of hydrogen is better because it does not have any carbon. So everything you can use. Okay, so you can generate more energy from 1 kg of hydrogen than 1 kg of diesel, 1 liter of diesel, whatever weight wise, if you consider like that. Okay. Similarly, I was talking about this piezoelectricity in your shoes. If you put this piezoelectric device, and as you are going for jogging, you are running and giving pressure on your feet, then it will generate electricity. So that is also a renewable source of energy. Another very interesting thing which is very important for this electric vehicle which is coming. Earlier days,
in still now all our car, like petrol and diesel based car, we have a battery. You will see that you have to replace the battery every 2 years or so. They are running basically on the chemical battery, chemical storage battery. You will have this H2SO4, copper sulfate, zinc sulfate as electrolyte, and there will be these electron reduction, oxidation, and two different electrode. So it's good because it has very high energy density, and high energy density is something you require when you charge when you start the car. Then you see that when you put the key like that, then the battery the car starts, right? For that you really need this high energy density, which is what your chemical battery was giving. But then one of the bad thing about this chemical battery is that it has a very low cycle life. After many of this charging, decharging, it will degrade, and that's why you need to replace it after 2 years. But then if you are thinking about electric vehicle, that means there is no petrol and diesel, so you have to really charge the battery again and again, just like you had the mobile phone, right? You see, the initially you do this nice charging and discharging happens. After some time, what happens is that it gets discharged very quickly, right? After maybe using 1 year and all this. Another problem is that it takes time to get charged. Now, definitely nowadays you are going to petrol pump and then going and filling the petrol in 1 minute, it's done. But if you go and charge your battery, right, in the petrol pump, it takes a long time. So that is why what you need to have, that you need to move on from that battery to supercapacitor based battery, where you can have not only very high life cycle, it will also charge very fast. And based on how fast you can do, you can have something called exponential supercapacitor. So you just go to a charging station, you go, and within 30 seconds your charging is done, full charge. And nowadays you will find out many of the mobiles are also coming like that, but 10 minutes you will have a full charge. So that means they are doing something with this supercapacitor, and the supercapacitor actually takes into account many of these nanomaterials and stuff like that. And interestingly, one of my colleagues' story I can also share with you. आप लोग सब मूंगफली खाते होंगे, right? In particular Lodi times, and what you do is that you eat the मूंगफली and then you throw away the chilka, right? Now the chilka, you can actually, from the chilka, which is a waste material, you can actually make a very interesting carbon based graphene like material, and that you can use in this supercapacitor. So that means your supercapacitor will have then lower price, right? So very interesting thing you can do, and that is what I see. And already you will see in Chandigarh, it will have this EV charging station like that. It will solve the issue. And I think very soon, maybe 5 years down the line, you will see that many of us will be going towards electric vehicle rather than going for this petrol and diesel. So I hope you got an idea about what are the different sources of renewable energy which are currently going on. Maybe 10 years before, this was like all, a story, right? But now it's all reality. Another interesting thing about this targeted drug delivery, which I can say, as I was just telling you, normally, see, you have a tumor somewhere over here, right? What you do is that in today's delivery, if you take normal drug will actually circulate in entire body, right? But if you now take the drug in a small nanoparticle, you see, these are all your drug, you put it in a small nanoparticle, and what you can do is that in the nanoparticle, you can also put a fluorescent probe. You can also monitor that where is the drug going in your body, just like people do this angiogram, right? If you have done ever, your parents, if they have done any angiogram, you will see they can monitor which part of the body the drug dye molecule is going. So you can actually monitor everything, where in the body the drug is going, how it is treating. And on the top of that, if you can write a address on the drug and the nanoparticle that, look, the tumor is in somewhere in, let's say, stomach, you go only there, you don't go anywhere else. So that you can do. Or how can you do that? It can auto recognize, like it can recognize, if you look at your healthy cells in your body, so there is not much of intercellular distance. But if you have a tumor cells, because of the growth of the tumor, you see that there are a lot of these intercellular distance where nanoparticle can easily penetrate through diffusion. This is another passive mode of selecting where is the tumor, right? Or other thing is that tumor cells are typically, the pH is little lower. That means they're acidic in nature. So if you have nanoparticle which sense this change in acidity, it can also go and end up in this. Otherwise, in the nanoparticle, you can also put some magnet. So you can make your nanoparticle magnetic nanoparticle and apply an external magnetic field so that it will go and accumulate over there. And you can see that you can actually put your nanoparticle through injection, it will circulate in your entire body. But as soon as you put a magnetic field, it will all go there in that particular tumor, and it will inject, and it will actually heal it very quickly. Okay, so this is how you can actually this is called targeted drug delivery, right? So these are different things we have learned. Okay, now what we will do next 5 minutes, we will learn something very interesting, because how we being scientists, we would look at the nature and we learn from the nature that what are the nanomaterial already present in nature, and what as a scientist we are doing, we are trying to mimic this, right? So this is again, let's get the scale. This is a meter based scale, this is millimeter, then it's micrometer, and this is nanometer. This is where is the scale we are going to look at. Now look at this natural world. You have all seen this. What is this? This is the ant. An ant, you can see this is in some small centimeter region, right? But then human hair you can see, and this is the last thing or the smallest thing with our naked eye we can see. This is one particular human hair, which is hardly something like 10 to 50 micrometer range. That is what your eye can see. But if you go below that, then what is that? You will come into your cells, right? What is that? Red blood cells. Red blood cells, what are the size? 2 to 5 micrometer. You cannot see red blood cells through your naked eye. What you need to do is that you need to see microscope. What is that? In your college also you will have that kind of microscope called optical microscope. Okay, but then if you go further down, that is something called DNA. Okay, DNA is actually the actual nanomaterial. You see that this is like 1 to 2 nanometer in diameter, and length may be a little more higher, maybe it will be 2-3 nanometer. If it is coiled, then it will be like that, 3-4 nanometer or something like that, right? So DNA is the actual nanomaterial. But can you see DNA? Have you seen DNA through your optical microscope? No, right? For that you need to take, so this is in nanometer dimension, right? Similarly, looking at this, you see man also made something like head of a pin. If you look at that, is also like 1 to 2 nanometer. Then you can also have this MEMS device. These are micrometer division. But then, as I was talking about these, these buckyballs or fullerene, that was like a nanomaterial. Similarly, later on, people also, scientists, they found something called carbon nanotube. Okay. Now, carbon nanotube also has a diameter of 2 nanometer. They are very small. It is actually comparable to the size of nanometer. Okay. Now, in this regard, I would like to also say, very interestingly, earlier days, you always know that, okay, how many allotrope carbon has? Maybe anyone can say how many allotrope carbon has?
3.
Who can give the answer? Yeah, what are they?
Graphite.
Yeah, come again.
Graphite, diamond,
yes. Third one?
and fullerenes.
Fullerene you came to know because it was 1991. But in 2000 onwards, I can tell you, but you should not write this in your, what you call is that exam sheets or something like that if it is not updated in the books. Science advances that way. I mean, something new will come, it will then come into your books. It will take some time, but I think at this moment you don't do. So graphite, you said. Now, what is graphite? Graphite has different layers, right? All sp2 carbon, sp2 hybridized, right? Now, if you take a scotch tape, or if you take a sellotape and put it on this graphite, which is where your pencil is a graphite, right? Put it, and then suddenly you peel it off. What you will get is that one layer of graphite sheet, and that is something called graphene. And this graphene is actually also a wonder material. You know why? Graphene can conduct electricity just like anything, better than even your copper wire. Copper wire, all this you put in copper wire, right? Electricity. And if you pass electricity, what happens? If you pass electricity, copper wire gets heated, right? Why does it get heated? Because
Because it's a good conductor.
Because of the resistance, right? You put voltage, current passes, but there is also resistance to it. Because of the resistance, it gets heated, right? So now the interest, that means you lose some heat. Okay, you lose some energy through heat. In the electrical energy gets converted into heat. But then interestingly, if you have graphene material, there you can really make very interesting, like there is not much of resistance. If you can use graphene sheets, they are super, yeah, they are very good conductor of electricity. That's what I can say. Similarly, carbon nanotube is also another allotrope. So graphene is another allotrope. Carbon nanotube is also another allotrope. And why it is important, and it has actually revolutionized the field, because carbon nanotubes are very light, because these are all carbon. Okay, now you tell me now, what is the strongest known material you know? Anyone?
Diamond.
Diamond is a good, but diamond is very
Diamond.
expensive. The diamond is, yes, you're right. But then other than diamond, typically you use it in regular days.
Graphite.
Iron, right? It's not actually iron, it is
Iron.
steel. Steel is the strongest, and that's why all these bridge, everything you make with the steel. And what is the lightest material known, which is also heavily used? Aluminium, isn't it? And that is why you will see many of the spacecraft, even you are traveling by plane, that is made up of aluminium body, right? Now, the problem is, you know, when you are, very interesting thing, perspective, I can also tell you this, that, you know, when you are flying in the aeroplane, I'm sure that many of you have this experience. If you look at the outside temperature at that particular height, it will be something like -20, -40, something like that. And if you're taking international flight, it will be much higher, and then it will be definitely like that. And here at the ground, we have temperature which is like 30 degree. So there is a difference of almost like 80 degree or 100 degree Celsius, right? What happens in metal, if you change the temperature so much, then what will metal do? Metal will contract and expand, isn't it? And this is the problem when ISRO is sending rocket from Sriharikota, which is in Andhra Pradesh, which is like 40 degree Celsius, and it is reaching up in the sky and in the space, which is really, really cold, you know, -70 or something like that. So you have many of the times, because of this expansion contraction, these rockets may, you know, get scattered into pieces. So you need to have material where you will have very low thermal expansion or contraction coefficient. Do you get it? And it should be also light, but it should be also strong. Carbon nanotube is one such wonder material. It is very light, and you won't believe this is actually comparable to the steel in terms of the strength. Okay. And third thing is that it doesn't have that thermal expansion, this thing. So this is a wonder material nowadays. That is why many of the flight, and if you remember, Air India has that bigger flight, right? 787 Boeing. Boeing is a company. So you have Dreamliner. So many of the, you know, interesting features in that particular Boeing flight is that they are also made, apart from aluminum, they are also made from the carbon composite. And you know what is that carbon composite? This is the carbon nanotube. Why? Because it will make it lighter. Okay. And if the plane is becoming lighter, then it can carry with the same weight, because you see, how do plane fly? Because it has to replace the similar amount of air, then only it will be able to fly. So it has to be lighter. And if it is lighter, with the same weight of the plane, you can carry more amount of people, and if you more number of people, and if you can carry more number of people in the plane, definitely the flight fare will come down, right? So this is a different perspective, and this is how you can see the nanomaterial, the growth of nanomaterial is helping our economy as well. Do you get it? So these are things I wanted to tell you. And now one interesting thing I wanted to tell you, as I was saying, that you know, red blood cell, you probably have this microscope in your college. This is optical microscope, you can see that. But then how do you see things like you are seeing me? How you are seeing the visible light which is falling on me, and then after that it is going into your eyes and you can see. Remember one thing, if you have to see me, my dimension should be much more than the light dimension, right? So what is the light, visible light? What is the wavelength of visible light? Anyone? It's around 400 to 600-700 or something like that. So light will come and fall. So nanometer, that is nanometer. I am in meter, right? Similarly, if you take red blood cell and all this, they are like 2 to 3 micrometer, means 2000 to 500,000 micrometer. But still, the wavelength of light is lower than that, so it will fall on that. but your eye cannot distinguish. That's why what you do is that through optical microscope, you actually put an objective lens so that it can actually make your, seeing better. That's what you do in your college. But now when I'm asking, okay, come, can you really see a DNA? Now the problem is DNA is already 2-3 nanometer. And if you talk about visible light is, let's say 400-500 nanometer. What I said, if you have to see something, the light dimension should be lower than that. Now you cannot see it. So what you need to do? So you have to use something called electron microscope. And I think you have already studied de Broglie's principle, wave particle duality. So you may conceive electron as a particle also. It might be a wave. It's like a light, right? An electron is very small, and they are much smaller than nanometer. They are much smaller than angstrom as well. So electron, if you use as a light source, then you can actually see very nice of this nanoparticle. And that is why this is very, very important, and it's quite expensive machine, like 4-5 crore. If you have to see nanomaterials, which are there also in our place, I think if you make a visit sometime to our institute, which is definitely possible any point of time, we will show you all these different equipments. And as soon as this got discovered, this particular machine was invented rather, then a lot of this nanostructure in nature and interesting applications that we came to know. Earlier days, we know that why the leaves are green. We knew that leaves are green because you have got chloroplast, and chloroplast is a pigment. So what it will do, light falls on chloroplast. Chloroplast will absorb everything other than green light. That's why green light will fall in our eyes, and you will see that is actually leaves are green. Similarly, you see carrots has carotenoid, and because of this double bond, this particular one, they will actually, you will see these carrots as orange because they will absorb everything other than that particular one, and it will show like that. Similarly, anthocyanin, different colorful. So all these are related to different pigments. That's what we knew. This is how color originated. But then when we looked at the butterflies, and people were looking at butterfly wings, and they're very nice colors. So people wanted to know how butterfly is so colorful. Can we really know the pigment? What are the pigments which are there? So what do? So you take the butterfly, kill it, and then all these wings, you put some solvent, and you can do this extraction method, which is what you do in plant extraction also. And you will get those chemical compounds, right? And you have to analyze the chemical compounds. What are these chemicals? But then they were saying, scientists were saying, all the cases chemical compounds are more or less same. Then how the colors were different? This they could not really answer. But then when the electron microscope came, then people started looking at these butterfly wings under this electron microscope, and they could see different levels. And you see there's electron, these are fins, and then you can see that there are these thin fins, and if you closely look at, you see there are actually in the fins, you have these small thin fins, and then you have this periodic, these are all void spaces. These black things you see, these are nothing. These are all void spaces. And because of this periodicity, very interesting things happens to the light. Now I want to give you an example of your class 7, whatever you read. What happened if you take a bucket of water and you take a stick and you put the stick in the bucket of water? What happens to the stick? What happens? It looks bent, right? And why does it look bent?
Refraction.
Refraction, because water has a different refractive index and air has a different refractive index, and that's why at the interface it looks bent. Now think about it like that. Similarly, here also you have a different refractive index over here, and these things, if it periodically continues, because of this number of periodicity, you can have a net refractance, net refractive index, and that is something called reflectance. And because of that, you can change the color. So this is the origin of color, and this is pretty new. This was only in this particular paper, and when they came in 2003, some Japanese scientists actually discovered that this is the origin of the color. And you can look at this particular, paper from the website, and you can see that that's how butterfly color gets originated. Now, this actually led to scientists that, this is the way we can actually make photochromic material, and we can develop different colors and all this. So this is what is very interesting, and scientists are working on this kind of thing. And in fact, we have also started working on this particular, photochromic field very recently. Last 1 year we have been working in our group. So I'm not going to discuss that particular field here. But then another very interesting thing, you can see that lotus leaves. What you see in lotus leaves, if you put water on this water takes a shape of a droplet. And if you put it on any other surface, water actually all smear across, right? But in this particular case, you see that this is droplet. And why is it so? But earlier people used to say you have a layer of something, wax or something like that. That's what we used to believe. But now if you look at through electron microscope, yes, there is a layer of something, but then you see they form this kind of nano beads like things. And that is why for the surface tension, what happens is that this particular water droplet, they sit such a way they can minimize this contact. And that is why you will see in this particular, you can measure this contact angle, and the contact angle is actually 160 degree. That means it is super hydrophobic surface. Typical surfaces, if you see, that is actually less than 90 degree. Okay, like 75 degree or a 60 degree or something like that. And this is something called super hydrophobic surface. Okay, now this is very interesting because, that is how you can see lotus leaves always keeps itself clean. Because if there is some dirt on it, and then you spray some little water or rain happens, it will take the shape of a water droplets, and the droplets will take away all the dirt. And this is how it happens. You see the red dirt, it will be taken away by the water. And that's how it is actually self-cleaning surface. Then scientists thought that's very interesting. I mean, we can, if we make a pattern nanostructure on any surfaces, then this surface will be self-cleaning. And based on that, people started making, the what you call is this shirts which are self-cleaning in nature. Okay, and you see on the shirt people made, and they did something kind of a nano finishing using certain kind of nanomaterial, and you can see your water droplet sits on the shirt like this, just like the lotus leaf. So you can think of, so this is how you don't need to really wash the clothes. Okay, now why I'm saying this? Similarly, you can also have a jeans which will also be self-cleaning. Now I will tell you what is self-cleaning. So if you are wearing some clothes for multiple days, two ways it gets actually dirty. One is that there will be a lot of this dust particle which actually gets accumulated on your shirt. Other thing is that a certain part of the body, you actually tend to develop some microbes. Okay, and those microbes also create. So these are, if you have to get your clothes clean, that means you have to take care of the darts, and second thing, you have to take care of the microbes. How do you do it? Now think about it. If you are in let's say Leh Ladakh area, okay, or maybe in Siachen Glacier, so you will have everywhere snow, right? You have plenty of light, but you have plenty of snow around it. So you might develop some bacteria and all. So what you do is that you do the nano finishing with TiO2 nanoparticle. Now TiO2 nanoparticle is very interesting as it abstracts sunlight. Okay, and it becomes antimicrobial in nature. It starts cleaning bacteria and all. So every day you come from your duty and you take off your shirt and put it in light, then TiO2 nanoparticle will kill all the bacteria, right? And if you are, suppose if you are in a BSF Jawan in Rajasthan desert or something like that, there is not much of water, so you cannot clean. So you might have a lot of dust in your thing, so you will have very limited water. So you cannot wash in washing machine. What you can do is that you can take little bit of spray, and because of this self-cleaning nature, just like lotus leaf, with very minimal water uses, this will get cleaned. Of course, TiO2 nanoparticle will also kill the bacteria, right? And this is why these are very interesting and important material for defense, because for our armed forces, they will not have all the luxury to use the washing machine when they are in duty or something like that. So these are all called self-cleaning fabrics. So this is very interesting. Similarly, you can also think of the water spiders or something. They nicely walk on the let's say water surface, which we cannot do, and that has to do with their if you look at their micro hairs which are there in their toe, that actually walk against the buoyancy factor, and that actually let it actually walk. And that's what, if you progressively see, if you take a beetle to, let's say, gecko, and if you look at the toe, and their the nanostructure pattern, from this very crude pattern to nanostructure pattern, that's how they can actually stick them onto the wall because of this air pressure. Now looking at this, scientists thought, very nice, then we can actually make very interesting polymer nano composites, which will, so if you can make them very patterned and very nice nanostructure on the surface, then we can actually make very nice, what you call is that Gecko tape or adhesive. And this is what actually people are working, including us. We are working on this kind of things. And you see, this is like a sticky note, which you write something, a note, and stick it onto it. This has this kind of polymer adhesive. Because earlier days, when you used to go to post office, there used to be that natural gums and all this, right? Rubber secreted gum and all these you used to use. Nowadays, we have become smart. We are using these polymer adhesives, which are very easy to handle. Another very interesting thing from the nature you look at, you might always think that, suppose if I ask you guys, okay, go and dip your legs in Sukhna Lake for 2 days. If you dip so, after 2 days, you will have that, you will have fungal growth around your legs. Okay. But now you might wonder, okay, how these sharks or fishes, which are always there in the lakes or in, under deep sea, why they are not going fungal infection? Why is it so? So very interestingly, this is also has to do with the nanostructure scales in their on their skin. Now what they do is that they have on their skin, they have these scales, okay, and there are these gaps or channels. So now what they do is that when they swim against the water actually passes through the pores. It's like you are in your garden, you are watering the plants, so you have a pipe. So if you tap the opening of the pipe, then it will go in force, right? Water jet. Same thing happens here. And water will flow very fast because of the channel, and because of the turbulent flow of water, no bacteria or fungal can actually ever develop in your body. Now, scientists, they observed it, and then they thought, okay, fine, can we really make very nice this kind of nanostructure? And in fact, this person from Northwestern University from US, they did it. And they saw that, oh, very nice, you can do very nice. But then another thing is the direction of the water flow is also very important. So you see, in this case, water flow is this direction. So it will be going through the channel, and you see no bacterial growth is possible. But if you can align it in a completely right angle, 90 degree, something like that, then you will see that channel flow of water will not be that efficient, and a lot of bacteria will start growing. Bacterial colony will grow. So then, based on this particular technology, because of this fluidics technology, one company only he created called Sharklet, and they are making very nice film or something like that, which will be antibacterial in nature. Now you can think of it, how it can actually have an implication elsewhere. Now you can think of that, if you are talking about shipping industry, you are making big ship or boat, right? Ship or boat. Now what happens? All the ships and boat, half of their area underneath the sea, they always stay underneath the sea or water, right? Now, if you can have very nice of this coating underneath, then what will have? They will have exactly like this, shark skin channel creation. So no fungal infection, fungus or anything will ever, create any issue with this underneath of the ship or boat. So they will last longer. So you basically save taxpayers' money. So there are very interesting things you can actually think of, and based on what you perceive and what you understand. And now I'm just coming last, how much time do I have? I have, I think, 15-20 minutes or something like that.
Yes, sir.
Acha, 10 minutes or so, I think. Let's, okay. All right. So now, these three gentlemen, they actually created very interesting. Now I was talking about Richard Feynman. 1959, he said there is plenty of room at the bottom. But then what happens is that these three gentlemen recently, in fact, I know these gentlemen very well because my office in Netherlands was just one office away from his office. He developed this kind of nano car. So he made molecules, and this molecule, if you shine light, it can start moving. And this gentleman, they made something called nano lift. You can think of that molecular motion. You made some molecule, this molecule, as if the person comes in and the person goes out, right? Now, this is very important, and that's why they got this Chemistry Nobel Prize in 2016. And why is it important? This is important because you can think of, as I was saying, you are having nanoparticle and you are putting drug into it and injecting in your body, and then they are going and delivering it. You can think that these are like a nano robot. You are attaching the drug in the car will enter. It's a nano car. Its in dimension is nanometer, 2-3 nanometer dimension. It will go, it will deliver exactly where the tumor is or wherever you need it to be. It will go, show it to you, or you can also put a very tiny camera also onto it. It will show everything about it. So something about laparoscopy, right? So it is something in next generation laparoscopy you can think of. So this is why this has a very big implication in maybe 10-15 years down the line. That is why these people got Nobel Prize. And now this is very important. So that means what they did is that they made a covalent synthesis of the molecule, because I suppose you are all chemistry graduates, so you would know what is the synthesis. Now they did some covalent synthesis, and now covalent synthesized molecule, they kind of assemble 4 or 5 molecule, and that's how you actually make the nanomaterial. So this is called bottom-up approach. Okay, and physicists always take a material and they keep breaking it and eventually go to this nanometer dimension. That is called top-down approach. But bottom-up approach is much more fascinating, and we, being chemists, we perform that. So what you do is that you do covalent synthesis, and the covalent synthesis, you actually take many of this covalent molecule and using supramolecular chemistry. Now supramolecular chemistry always entails non-covalent interaction. And what are these non-covalent interaction? You must be knowing about hydrogen bonding, pi-pi interactions, right? Ionic interactions. These are pretty much in non-covalent interaction. And in covalent interaction means where you form a covalent bond. So next 10 minutes or so, I am going to give you some flavor of what we do and what you can actually, this might be a little complicated. So what I will do is that I will just show the slide and tell you the gist. I will not go into much more details. So what happens, what we do is that we take these atoms and we make these molecules. And now what we do is that using non-covalent interaction, we do this supramolecular aggregate, right? And this is how, if you can use biomolecule, it can actually go for cellular, you can develop artificial cells or biological intelligence. If you are using normal molecules, you can go for artificial intelligence. And that is the direction we are actually going, right? And this slide is very busy, and still I can tell you this is what in my group in INST we are working on. Little bit I can tell you, we are in our lab, what we do is that we look at nature, we learn from nature, and we want to do looking at the nature things which can be nature mimetic. Okay, so what we do is that we see the protein, right? Now what we see is that protein actually normally very nicely fold into certain native form of protein. So we thought, okay, can we now make a very interesting single chain polymer, and we can put some functional group into it, and we apply some stimuli, and it can form some kind of protein folding mimic. So that is what we do, and we can make very small nanomotor. Not only that, can we really make some polymer coating, and using some stimuli, can we really make the polymer coating? If you make a cut on the polymer coating, the cut automatically heals. So that is something we do. Now, these are very interesting thing we do. Other than that, we also work on peptides. What are peptides? You must be also reading about it. Peptides are nothing but small amino acids, and they are the basic building block of proteins. Okay, and we do many of these interesting things, and we make hydrogels. So hydrogels are like, you take this material, put little water, and what will happen? Water will become like a solid material. And pretty much this is what happens in your baby's diaper, and that's how actually baby's diaper, you have this hydrogel material. It will soak all the water and it will become solid mass. Now that particular hydrogel material we are actually using for doing tissue engineering. Peptide polymer conjugate we are taking, and we are doing hydrogel scaffold. We are trying to do like extracellular matrix, which is there present in your body. We are trying to artificially make organs or tissue. Okay, these are different, and these are the people who are working tirelessly in our group. So some of the interesting example I can give you, like self-healing, as I was just saying. The nature has this own way of doing self-healing. You see, sometimes you make a cut in the tree, and the tree actually secretes some kind of latex secretion, and it actually protects itself against, let's say, a fungal infection or something. In fact, your body, if you look at the body also, you make a cut, you will see that after some day it will automatically heal. Your body is very fascinating soft nanostructure, actually, to be very honest. So multiple people try to attempt this with some synthetic material. Some people, what they do is that they made a very nice polymer film and they put something, one small capsule, and in the capsule they have some healing agent. Whenever you make a cut, the wall, what will do, capsules will get broken, and then all the healing agent will come and it will actually cement, right? But then the problem is that the capsule, in the capsule, whatever healing agent is there, that will be released, right? You can heal it only once. So how can you do this healing again and again, multiple times, just like plant does or our body does? Now for that, what you need to do is that we have to do our kind of material where you do supramolecular chemistry using many of these interactions like hydrogen bonding interaction, host-guest interaction, something like this. So what we do, just to show you, is that we make, this is typical organic chemistry we do, and I don't want to go in details. We make these different polymers, and in the polymer we actually put this kind of coumarin functional unit. This is called coumarin, and the coumarin functional unit is very good because if you shine light of 320 nanometer, it will form this dimer, and if you shine 250 nanometer, 254 nanometer, it will also cleave. Okay, now if you form a dimer, they will become rigid, and if you again cleave, it will become very flowy material. Now using this, we actually do very interesting thing, and we actually follow it using some interesting technique called DSC. We can see that this become rigid or it becomes softened. And using this, what we do is that, you see, this is the polymer film you do, and you make a cut on it. And as you make a cut, you see nothing happens. It cut remains like that. As soon as you shine light 254 nanometer, what it will do, this coumarin dimer will get into coumarin, and then quickly this cut, as you see, the molecular diffusion will happen and the cut will get healed. Okay, not only that, this polymer film, whatever we have coated, we see that these are pretty much hydrophobic in nature. Now, why I am saying all this? I was telling you some point of time, you see the solar cells, nowadays we are coming up with next generation solar cell, which are not silicon. These are all perovskite material or something like that. They are moisture sensitive. Or acid rain. If there is an acid rain or something like that, it will damage the solar cells. So what you need to do is that you need to put a coating above it. So coating should be hydrophobic so that moisture, oxygen, they will not kill your perovskite material, and it will give a very nice solar cell behavior. And second thing is that your polymer should be transparent to sun so that the solar cell efficiency also stays intact. Okay, and not only that, even if there is a cut, it will self-heal. Suppose there is a bird will come, it will come and sit on your solar cells. It will do some, it will pass some shit. That means what? That is a phosphate, right? And the phosphoric acid will be acidic in nature. So that will, if you have a coating, it will not damage your solar cells. Second thing is that because of this bird claw, it might damage the solar cells thing. If you have a polymer which is self-healing in nature, it will automatically heal. So that means your things will last long. So you will get unhindered solar cell energy. This is one application you can think of. Similarly, we are also now working, this is in work in progress, I don't want to show, but I think you would be knowing many of the electronic gadget you will be using, or that earplug. After some certain days, you see that the earplug does not work. And this works because of an effect called electrical treeing effect. Because of that, you in your polymer matrix of the, let's say, whatever your earplug and the wire, they will generate some tree like this crack. This is called electrical treeing. And we are now developing some magnetic nanoparticle based stuff which will locally heat it and repair it automatically so that it can last long. I don't want to go in details. This is called magnetically self-healing. So this is some of the things we are working. Now, another very interesting thing we actually have worked, and I can tell you a little bit in 1 or 2 minutes, and this is inspired by looking at my son 2 years ago when he was having very high typhoid. And because of the typhoid, what happens if you have ever have a typhoid, you see that your temperature of the body shoots up very rapidly. And because of the shooting up, what happens is that you might faint also. So you need to immediately get paracetamol and all this. If you don't have it, that's it. So I noticed it. Then I thought, okay, can we make a material? If we can make a polymer, and we make, because of this protein folding, and we make these small little nanoparticles, which is like less than 30 nanometer. So smaller the nanoparticle, it will circulate in your body for longer time. And in fact, these are the material which are good for, delivering in the brain and also delivering for ocular delivery. Normally what happens, you have this blood retinal membrane or blood brain barrier which will actually not allow your drug to go and deliver there. Okay, that's why it becomes a little difficult to treat or deliver drug in brain or eyes. So if you have a very small nanoparticle, less than 30 nanometer, that can cross the thing. And not only that, you can actually have a prolonged circulation. I thought, okay, can we really make a small, let's say, nanoparticle, and in that, if we can put this antipyretic drug, as soon as your body temperature shoots up, the nanoparticle will be intelligent enough that it will actually understand, oh, it is shooting up, it will automatically deliver that drug, and body temperature comes down. This I actually got inspired looking at my 6-year-old son that point of time, and this was the thing my student Jojo, he actually worked on, and he showed that as the temperature goes around 40 or so, there is some change happens in the nanoparticles and drugs might come out, and we could show that drug actually suddenly, otherwise drug does not get released. As soon as heat it up, drug gets released quickly. That's what I wanted to tell you here. I'm not going into much in details. You can see the nanoparticles, which are very small, 16 nanometer in size, these round shaped ones, right? So these are various things I wanted to say, but I think I don't probably have much time. So I will skip some of the things which we are also working on, very cool stuff, like that maybe on some other time I can tell you, because it's very difficult to really tell you in 1 hour time frame, multiple interesting things which are going on in the lab. But few gist I can say, we are trying to also find out how origin of life happened and how nature is very interestingly making such kind of very precise nano, let's say this is a honeybee, the very specialized hexagonal matrix nature is automatically making, or the ice crystal. Why human we cannot make? I'm not going to discuss this, but in our group, we are trying to make all these kind of very precise nanomaterials using small peptides. We can actually make nanoparticle, then we can make nanofiber, we can make nano sheets. These are all very useful, and this is how we can actually make very precise. I'm not going to discuss this because I don't have time. What we are going to do, just last 2 slides I want to say, is that using this very nice peptide, peptide fibers like that, you can see, and they are also very relevant to many of the biopolymers which are found in our body. So we are trying to look at, can we really grow tissue on it? So for that, we are actually working on these hydrogels, and you see this is a solution. But if you have hydrogels, even if you make the vial ulta, you see they will not flow. And using this as matrix, you can actually go for very interesting wound healing. You can go for, or you can actually develop. You see your ear got, you want to replace your ear using this 3D printing, and using this kind of scaffold, you can actually print your ear. So these are actually the application of hydrogels. And these hydrogels are actually used in wound healing, because hydrogel has mostly these water molecule only, except some of these fibers. You see, you have got a burn in the mouse, okay, and you see you do the normal dressing as you used to do earlier days, it will heal, okay. But if you do with the hydrogel, you see it will heal much better in couple of days. So your healing gets better, it's the wound healing. Similarly, what we are doing in tissue engineering is that if all these peptide based nanofiber, nanometrics, what we make, and hydrogel we make, we take stem cells onto it, and then what we do, we grow the stem cells, we develop the organ using 3D printing, and then we can replace the organ in human body. That's the thing, that's the direction, that's the plan we have, and that is the direction we are working on. And some of the things we are working on in this direction is that, let's say, the bone, so this is bone tissue engineering. So what bone tissue engineering, very particularly, like you have extracted your tooth, right, and now you are putting some implant, but that is artificial material. Now I'm thinking, now can we really make the implant material such, which is like a silicate bioactive glass material, we put it there, now it will be there, you are regularly using it just like that. After 30 days, that particular artificial material will convert into your natural tooth. How cool is that? So that is that in that direction we are actually working on bone tissue engineering, and we have shown that we can make this peptide, we can mineralize this peptide with silicates, and we can use that, and this will eventually form bone-like species. This is what I can tell you. We don't have to really look at all these different difficult chemistry. That is maybe some other time when I give a very specialized talk, I can tell you. And not only that, another very interesting thing we are working that in collaboration is like, you know, many of the people, old age people, they have this knee issue, घुटनों का दर्द, ठीक है ना? So many of them actually go for knee replacement or knee transplantation, which is a very, you know, painful process. It takes a couple of months. We are trying to use some of these hydrogels, and what happens, can we really inject some of these chondrocytes which are there present in the cartilage tissues? Can we really inject, and then can these, you know, these artificial matrix promote the growth of cartilage, which will actually heal your knee? And if it is happens, then you just have to take a couple of injections. That is good enough. You don't need to really go for replacement. So this is the direction, and we are, you know, trying to work, and we are getting some initial success. Similarly, another last thing, and this is just came under minor revision from this interesting American Chemical Society journal. So can we now make artificial muscles, which are very important for, let's say, your heart? Heart always beats, right? Systole, diastole, you already studied, right? Now, very interesting thing is that most of the hydrogel, what you make in our lab, if you apply force, what will happen? They will become liquid in nature. That is normally called strain softening in nature. Same example you already every day you do in the morning when you wake up, you go for this brushing teeth, right? What you do, you have a toothpaste. So toothpaste you press, so you are applying force from toothpaste is coming from the mouth, right? And then after that it is getting released, and then again it is getting solidification. So this is actually a strain softening behavior. But then if your heart muscles or your blood vessels, if they are strain softening material, then what will happen when you are putting pressure? Then what will happen? They will become like that, and they will never be able to pump the blood throughout your body. So what you need to have a very interesting material and material property that should be is strain stiffening material. So you apply force, this will become stiff, and that actually no one, at least in India, no one has made such kind of material. And we are trying to make such kind of material using our peptide and polymer conjugate. And you can see that if you are heating it up, or if you are applying some strain, you see this is shooting up. So this is what we are now working on. So that can we really make artificial muscle cells or something like that. Overall, this is what I wanted to tell you. So we have learned a lot of this interesting thing. I showed from my, you know, these are what I'm summarizing for last 15 minutes, what I said. We made some polymer coating, which can nicely self-heal. And if you can self-heal, you can use for these, you know, solar cell applications or devices. I showed that many of these polymer peptides, which you have used, they are very functional in nature. Sometimes you can make this fiber, you can make this sheet. This we can use for various applications. You can go for biomineralization for bone cell or strain stiffening material, as I was saying. Not only that, I did not also discuss at all many of these peptides, because of they have this amide bond. You can actually generate very interesting piezoelectricity from here. So not only that, you have a cardiac heart muscle generation, they will be also generating electricity from that heartbeat. So these are some of the material we are developing, and I would like to thank all my collaborator and you know, this interesting bunch of you know, people I have in my group. And you can see as a young group, the group was smaller, and now this is hardly a 7 days or 10 days old picture. These people are happily enjoying and also working in my group. And I have this generous funding from all these different funding agencies to support what I actually said in last 15-20 minutes or so. Thank you for patiently, you know, listening to my talk. And I think if you have any question, I'll be very happy to answer. So with this, I would like to finish rather long, lengthier one. So yeah, thank you.
Any questions?
Yeah, I think I would like to really interact. If you have any questions or any kind of thing you want to ask, I'll be very happy.
I invite Dr. Shifali Dhiman to say a few words.
Thank you, Dr. Nisha. So on behalf of the entire NCM fraternity, our honored principal ma'am, Dr. Nisha Bhargav. I, Dr. Shefali, head postgraduate department of chemistry, thank Dr. Ashish, scientist F, INST Mohali, for sparing his valuable time with us and giving an insightful and a very knowledgeable lecture on nanotechnology and its future implications. The lecture is being sponsored by Department of Science and Technology and Renewable Energy Chandigarh as we are celebrating Science Week in our college. I'm sure the impact of nanotechnology is expected to exceed the impact that the electronics has had on our lives. It was an idea that most people did not believe. So the future of science is nanotechnology. Thank you, sir, once again. I'm sure our dear students have really enjoyed a lot. Over to Dr. Nisha for an official vote of thanks. Thank you so much.
Thank you, ma'am. Thank you. Good afternoon, everyone. On behalf of Honorable Convener and Principal Ma'am Dr. Nisha Bhargava, Dean Sciences and Co-Convener Dr. Indu Arora, Coordinator and Head of Department of Chemistry Dr. Shefali Dhiman, I, Dr. Nisha Davra, take this opportunity to extend a very heartfelt thanks to Dr. Ashish Paul for his excellent and knowledgeable presentation on nanotech and its implications in future under the aegis of MCM Vigyan Manch to mark the celebration of National Science Day. Thank you, sir, for accepting our invitation and sparing your valuable time for enlightening our students with your words of wisdom and knowledge. And thank you to all the coordinators of this event for wonderfully coordinating this event. I am grateful to all the student participants who have joined us today for this talk of Dr. Ashish Paul. Thank you. Thank you, everyone. Thank you, sir. Thank you.
Thank you for hosting me as well. And I think we wish that some point of time you can also visit our campus.
Sure,
and
sir.
You're
Sure.
most welcome to visit and see.
Sure, sir. We'll come up with the PG students.
Sure. You can
So
always
just one
contact.
thing, it was an amazing lecture. It was a quite informative lecture that we can hear from like nanotechnology branch. So we could learn many things from you. Thank you.
Thank you, sir.
Thank you, sir.
Thank you.